For decades, fusion scientists had a problem that sounds almost ridiculous when you first hear it. They had spent billions of dollars learning how to create matter hotter than the center of the sun. They could trap that plasma inside magnetic fields. They could heat it past 100 million degrees. They could keep it away from the metal walls. But then they still had to answer one very basic question. How do you feed it? A fusion plasma is not a campfire. You cannot simply open a door and throw more fuel inside. The fuel is usually hydrogen or hydrogen isotopes, and the plasma is surrounded by magnetic fields specifically designed to keep extremely hot particles confined. So the fuel has to be injected in a way that reaches far enough into the plasma, responds quickly enough for precise control, and does not simply stick to the walls before it becomes useful. For years, one of the simplest answers was gas puffing. Open a valve. Release hydrogen or deuterium gas near the edge of the machine. Let the gas enter the plasma. Simple, cheap, reliable. But there was a problem. A lot of that gas never reached very far. Much of it was ionized near the outside of the plasma. Some interacted with the walls, and the deeper scientists wanted to fuel future reactors, the more obvious the limitation became. Another solution was much more aggressive. Freeze the fuel into tiny solid pellets and fire those pellets directly into the plasma at high speed. That can push particles much deeper. It can be extremely effective. But pellet systems are more complicated. They need cryogenic equipment. They need reliable pellet formation. They need acceleration systems. They need to work shot after shot without jamming or breaking. Then, in China, researchers came up with something sitting between those two ideas. Do not slowly release gas. Do not freeze it into ice. Take gas at high pressure. Force it through a specially shaped nozzle. Accelerate it into a directed supersonic molecular beam. Then shoot that beam into the plasma. The technique became known as Supersonic Molecular Beam Injection, SMBI. It was first proposed and demonstrated on China's HL-1 tokamak and developed further on HL-1M. Later, it appeared on fusion machines outside China. France, Japan, Germany, South Korea, the United States. Different tokamaks, different laboratories, different experiments. And now, decades after the idea was first tested, the International Organization for Standardization is preparing to publish ISO 19991, an international standard specifically describing the supersonic molecular beam injection fueling technique for experimental magnetic confinement fusion facilities. Think about that progression: a fueling idea tested on a Chinese tokamak, then copied, adapted, and studied on machines around the world, then turned into a formal international technical standard. That does not mean SMBI has solved fusion. It does not mean every future reactor will use only this method. And it does not mean the standard itself creates a power plant. But it does mean something important happened. China did not simply build another artificial sun. It invented one of the tools used to feed them. And if you enjoy stories where the most important breakthrough is hidden in the engineering nobody normally talks about, hit like and subscribe, because once you understand how hard it is to put fuel into a fusion plasma, this simple-looking nozzle starts to make a lot more sense. To understand the problem, picture a tokamak. A tokamak is basically a giant magnetic bottle shaped like a donut. Inside that donut is plasma. Not ordinary gas. Plasma. The electrons have been stripped away from the atoms. The particles are moving at enormous speeds. The temperature can climb beyond 100 million degrees Celsius. At those temperatures, no ordinary material can physically contain the plasma. Steel would melt. Tungsten would eventually be damaged. Almost anything touching the core plasma directly would be destroyed. So magnets do the job instead. Powerful magnetic fields guide charged particles around the donut and keep the hottest part of the plasma away from the walls. The goal is to create conditions where light atomic nuclei can fuse together. For the most widely studied reactor fuel, deuterium and tritium nuclei collide and fuse. The reaction releases energy. That energy could eventually be converted into heat and then electricity. But there is one thing experimental diagrams make easy to forget. The plasma needs particles. A future reactor cannot simply create one plasma and leave it alone forever. Particles escape. Fuel gets burned. Impurities enter. Density changes. The operators need to control how much fuel is inside and where those particles are deposited. That makes fueling part of plasma control. And the word control is important. Imagine trying to keep the pressure inside a jet engine perfectly stable while your only control is a garden hose connected 50 meters away. That is close to the problem with crude fueling. You do not just want more gas. You want the right amount. At the right time, in the right place, with a response fast enough that the plasma does not move into an unstable condition before the fueling system catches up. Traditional gas puffing works by injecting neutral gas near the plasma edge. The hardware can be wonderfully simple. A gas reservoir, valves, pipes, an opening into the vacuum vessel. But the plasma edge is extremely hot compared with anything on Earth. As neutral particles move inward, collisions ionize them. Once ionized, they start interacting strongly with the magnetic environment. That means many particles never penetrate deeply into the plasma core. So scientists faced a trade-off. Gas puffing is simple, but shallow. Pellet injection can go much deeper, but the system becomes more complicated. Chinese researchers asked whether gas could be made to behave less like a diffuse cloud and more like a projectile. The answer was a supersonic molecular beam. The heart of the system is a nozzle. Not a rocket nozzle in the dramatic sense, but the physics is related. High-pressure gas enters the injector. The gas expands through a converging-diverging nozzle. As it expands into the low-pressure environment inside the fusion machine, part of its internal energy becomes directed motion. The molecules accelerate. The flow becomes supersonic. Instead of gas drifting randomly in every direction, a much larger fraction moves together as a focused beam toward the plasma. This is the part that changes everything. Direction. Ordinary gas puffing is like spraying perfume into a room. SMBI is closer to firing a pulse of compressed gas through a nozzle, so the molecules share a strong forward velocity. The fuel is still gas. There is no cryogenic pellet to manufacture, but it enters the plasma much faster and more directionally than a conventional puff. Early experiments on China's HL-1M showed why researchers became interested. SMBI improved penetration and fueling efficiency compared with ordinary gas puffing. At high gas pressure, researchers observed beam particles penetrating toward the core region. Measured beam velocities exceeded 1,000 meters per second in some experiments, and repeated pulses could increase plasma density in distinct steps, producing behavior that looked more like repeated pellet injection than ordinary gas puffing. That was the key. The system was beginning to occupy a useful middle ground, more effective than simply releasing gas, less mechanically complex than producing and firing frozen pellets. Not as deep or efficient as the best pellet fueling in every situation, but easier to pulse, fast to respond, relatively simple, and useful for experiments where scientists wanted to change plasma conditions on very short timescales. Then something important happened. Other laboratories started using it. This is one of the best tests of any technical idea. A laboratory can claim that its invention works. A paper can show an impressive graph. A press release can call something revolutionary. But when completely separate research teams decide it is useful enough to install on their own expensive fusion machines, that tells you more. SMBI systems were later used or studied on major magnetic confinement devices, including Torre Supra in France, Azdex Upgrade, and W7AS in Germany, JT60U in Japan, K-Star in South Korea, the National Spherical Torus Experiment in the United States, the Large Helical Device in Japan, Heliotron J, and Chinese machines including HL2A and East. The exact implementations were not identical. That matters. Researchers adapt injector geometry, pressure, pulse duration, and location to the machine. A tokamak in Japan is not physically identical to one in China. A stellarator does not have the same magnetic geometry as a tokamak. But the underlying technique traveled. Japan's JT60U gives us a particularly clear example. During maintenance work in 2005, Japanese researchers installed a supersonic molecular beam injection system in collaboration with CEA Cadarache in France. Injector heads and a compressor were added. The system was prepared for efficient particle fueling. Later experiments used the injector and measured how the pulses changed plasma density and confinement. Think about the chain. The idea begins in a Chinese fusion program. French and Japanese researchers build their own version. It gets installed on one of the most important tokamaks of its era. Then the resulting data becomes part of the global research base. That is how a national invention becomes an international technique. And the more scientists used SMB, the more they discovered that it could do more than simply add fuel. Because a fast pulse of particles can disturb the plasma in controlled ways. That makes the injector a diagnostic and control tool. Researchers have used SMB to study transitions between different plasma confinement states. They have used it in experiments involving edge-localized modes, the violent bursts of energy that can strike components inside a tokamak. They have used it for density control. They have used it to study particle transport. In other words, the injector does not just fill the tank. It can poke the plasma. A controlled pulse changes local conditions. Scientists watch how the plasma responds. That response tells them something about transport, stability, and confinement. The fueling system becomes part of the experiment itself. This is why fusion engineering is so strange. A component that sounds like plumbing can become a physics instrument. A valve can influence confinement. A nozzle can change turbulence. A gas pulse can help researchers understand how a 100 million degree plasma changes from one operating regime to another. And that is where the story starts moving from invention to standardization. If you have made it this far, subscribe, because the next part is what almost never happens in viral fusion stories. A technology becomes important enough that engineers stop arguing only about whether it works and start arguing about exactly how everyone should define, build, test, and inspect it. Standards sound boring. That is exactly why they matter. Imagine every country built electrical plugs with random voltages and dimensions. Imagine every shipping container had a different locking mechanism. Imagine every computer network invented its own definition of basic data transmission. Technology can exist without standards. Infrastructure usually cannot. A standard takes an idea and creates a common technical language around it. What components are part of the system? How should the beam be characterized? What parameters matter? How should injection rate be verified? What inspections should be performed? What terminology should engineers use so a laboratory in one country understands what a laboratory in another country is describing? For SMB, that process became ISO 19991. The formal title is long because international standards are not written for thumbnails. It covers the Supersonic Molecular Beam Injection fueling technique for experimental magnetic confinement fusion facilities. The document specifies methods and requirements for the technique. It describes system components. It deals with beam formation and use. It covers parameters including gas pressure adjustment, beam characteristics, and injection rate requirements. And it lays out procedures for verifying those parameters. The project entered the ISO process in January 2024. Then came working drafts, committee review, comments, a draft international standard ballot, final approval. By July 2026, ISO listed the document at stage 60.00. International standard under publication. That detail matters. As of August 2026, the standard has cleared the approval path, but ISO still lists it as under publication rather than as a long-established final document already sitting on shelves for years. So the accurate story is not that the world has been following China's official SMBI standard for decades. The story is that a technique developed in China, tested internationally for decades, has now reached the final stage of becoming an ISO international standard. That is more interesting anyway, because it shows how long real engineering takes. The first proposal and demonstration came around the HL1 era. Development continued on HL1M. Peer-reviewed results appeared in the following years. International machines adopted the technique. Engineers refined nozzles. They measured beam characteristics. They compared fueling efficiency with gas puffing. They studied pulse timing. They tested different pressures. They used SMB in different plasma regimes. Then, Only after all of that accumulated experience, standardization arrived. This was not invention on Monday and ISO on Friday. It was decades. That is how mature technology actually grows. And there is another reason the timing matters. Fusion is changing. For most of its history, fusion research has been dominated by experimental machines. The goal was to learn plasma physics, make the plasma hotter, make it denser, hold it longer, understand instabilities, understand turbulence, improve magnets, improve heating. But the next generation is increasingly about reactor engineering. ITER is designed to study burning plasma physics on a scale far beyond previous tokamaks. China is building BEST as part of its next stage toward burning plasma research and eventual electricity demonstrations. Europe has demo concepts. China has its CFET plans. Private fusion companies are building their own machines. As fusion moves from experiments toward systems that may need to operate repeatedly and eventually continuously, boring engineering becomes more important. Fuel valves, pumps, tritium handling, maintenance robots, vacuum systems, heat exhaust, materials, diagnostics, control software. Every one of these has to work reliably. A future power station cannot require a room full of plasma physicists manually adjusting a custom experimental injector every time it wants more fuel. Systems have to become repeatable, maintainable, testable, interoperable where appropriate. That is exactly the environment where standards become valuable. But SMB also has limits. This is where the story needs to stay realistic. Pellet injection remains extremely important because solid pellets can deliver fuel deeper into large, hot plasmas. For a reactor-sized device, deep fueling is a major challenge. SMBI does not automatically replace pellets. Even the ISO material describes the technique as something that can complement other fueling systems rather than making every alternative obsolete. Gas puffing will not disappear either. It is simple, reliable, useful for many jobs. A real fusion device can use several fueling and gas injection systems together, different tools for different operating conditions. That is common engineering. A car does not have one control system. A power grid does not have one generator. A tokamak does not need one universal injector. So why standardize SMB if it is not the only answer? Because a technology does not need to dominate the entire industry to become infrastructure. Ethernet did not eliminate every communication technology. Hydraulic systems did not eliminate electric motors. Gas turbines did not eliminate steam turbines. SMBI can occupy a useful part of the fueling and plasma control toolkit. Its value comes from the combination: gas-based rather than cryogenic, directed rather than diffuse, fast response, pulsed operation, relatively straightforward hardware, and enough penetration to outperform conventional gas puffing in many experimental conditions. That combination is why laboratories kept using it. There is also a geopolitical angle, but it is more subtle than the usual headline. Fusion research is one of the few advanced technology fields where competition and collaboration exist almost on top of each other. China wants fusion leadership. The United States wants fusion leadership. Europe wants it. Japan wants it. South Korea wants it. Private companies want it. At the same time, fusion machines depend heavily on international science. ITER itself is built around international participation. Researchers travel between facilities. Scientists publish data. Components are developed in different countries. Experiments are coordinated across institutions. A technique can therefore be invented by one country and become useful to everybody. SMB is a clean example. Its origin is Chinese. Its development became international. Its standardization is international. That does not erase where it came from. It shows what technical influence looks like. Influence is not only exporting finished machines. Sometimes it is inventing a method other engineers decide is useful. Sometimes it is designing a component. Sometimes it is creating the procedure everyone eventually agrees to measure the component with. And in fusion, those small pieces accumulate. China has also become more deeply involved in international fusion engineering through ITER components, superconducting systems, plasma experiments, and large domestic facilities. So ISO 19991 sits inside a broader change. China is no longer only learning from the established fusion programs that came before it. In some areas, it is contributing technology that moves in the other direction. That does not make China the leader in every part of fusion. It does not mean one standard determines who wins the race to fusion electricity. There is no single racetrack. Superconducting magnets matter. Plasma-facing materials matter. Tritium breeding matters. Heat exhaust matters. Fueling matters. Plasma control matters. Economics matters. A country can lead one layer and struggle in another. But a technology that starts domestically and ends up on foreign machines is evidence of real technical contribution. And a technology that reaches ISO standardization has moved beyond a one-off laboratory trick. Take a step back and look at how simple the core idea is. Start with hydrogen. Compress it. Send it through a nozzle. Let the gas expand. Turn random molecular motion into a directed supersonic beam. Fire short pulses into a magnetically confined plasma. The machine is holding matter hotter than the sun. The fueling hardware can still begin with a valve and a nozzle. That contrast is almost perfect. Fusion is often described using giant numbers, 100 million degrees, gigawatts of potential power, magnets weighing thousands of tons, vacuum vessels the size of buildings. But the technology only works when thousands of smaller systems behave correctly. The future of fusion may depend as much on valves, bearings, seals, sensors, and injectors as it does on spectacular plasma records. And SMB is a reminder of that. The breakthrough was not creating fusion. It was improving one of the everyday jobs a fusion machine has to perform. Feed particles in. Do it quickly. Do it efficiently. Do it predictably. Do it in a way operators can control. Then repeat. China first demonstrated the concept on HL1 and developed it through HL1M. Researchers improved the method. Foreign facilities installed their own systems. Japan used it on JT60U. France used supersonic gas injection on Torre Supra and later West. Other devices adopted related SMBI systems. Chinese machines, including East and HL2A, continued refining the technique. The technology became useful not only for fueling, but for plasma control experiments. Then the engineers did what engineers do when a technology becomes mature enough. They wrote down the rules. ISO 19991 now defines the technique in a way laboratories and future fusion projects can reference internationally. That is the full story. Not China invents magic. Not the world immediately copies everything China does. Not SMBI replaces every other fueling technology. A better story. A real engineering idea survives long enough to become normal. And becoming normal may be the biggest compliment any invention can receive. The first time someone fires a supersonic molecular beam into a tokamak, it is an experiment. The 100th time, it is a technique. When laboratories in different countries build their own versions, it becomes a technology family. When engineers start specifying requirements, inspections, and common definitions, it becomes infrastructure. That is how technological influence spreads. Quietly. One component at a time. And if fusion power stations eventually operate day after day, most people will never know how their fuel gets into the plasma. They will not know the nozzle shape. They will not know the beam velocity. They will not know which research team first tested the idea decades earlier. They will flip a switch. Electricity will arrive. And somewhere inside a machine producing that power, a fueling system may be using principles that began as an experiment on a Chinese tokamak. If this video gave you something new to think about, hit like, subscribe, and turn on notifications. We go deep on the technologies that become important, long before the rest of the world notices them. And here is the question I want to leave you with. When we finally get practical fusion power, what will history remember? The machine that first produced electricity? The country that held plasma the longest? The company that built the cheapest reactor? Or the thousands of smaller inventions that quietly made the whole thing possible? Because sometimes changing the future of energy does not begin with building a new sun. Sometimes it begins with figuring out how to feed one.